In this video, we're going to derive the push-forward or Jacobian-vector product rule for the L2 loss. The L2 loss can also be seen as some sort of the squared L2 norm, and you typically find this in regression problems. It looks the following, so that you have a function that takes a proposal vector y as well as a reference vector y uppercase R here in that notation, and then it computes a scalar value by taking the difference of the two, then computing the 2 norm or the L2 norm and squaring it. Oftentimes you also see a factor of 1/2 in front of it. We will see later why this is helpful. Let's denote the output to that function with capital L, our loss. This is a scalar value. So let's make this explicit. We have both two vectors of the same size. So we have an n-dimensional y vector as well as another n-dimensional y reference vector. Then we have L, our scalar loss, and as such, the function L for which we want to define the push-forward or JVP rule takes both an n-dimensional vector and another n-dimensional vector and maps it to a scalar. And as said, such losses, they are typical in regression problems. So for instance, if you want to train artificial neural networks in order to find a regression surface to a function, which is really common application in scientific machine learning. If you want more details on why this loss is so common and how it arises as the maximum likelihood estimate under a Gaussian error assumption, I have a video for the linear regression problem linked up here. But this is not part of the video why this arises. Here it's more our task to propagate tangent information. And more precisely, we want to forward propagate. So we want to forward propagate tangents on the input, and there you read that we have a vector y with a dot on top, which is our tangent on the guess solution. It is another n-dimensional vector, as well as some dot input on the reference, which is also another n-dimensional vector, and we are asked to propagate this to the output, and then we will get an L dot, which will be another real valued number. Okay, how do we do that? In general, we have the rule for the push forward operation in that we find the tangent on the output, L dot, by summing over all the Jacobians of the function with respect to the inputs and then contracting them with the corresponding tangent information. So in our case, we have two inputs, so this will be two summands. So the derivative of the loss with respect to the guess vector y, and then contracted with y dot. So it is matrix vector multiplied if it was a Jacobian. So here it is the derivative of a scalar with respect to a vector. So it is not like a dense matrix with a lot of rows, but only one row in that particular case. Anyways, it will still be a contraction here. And then we also add the same with the derivative with respect to yr. So the derivative of L with respect to the reference multiplied with the tangent on the reference. So in either way, we have to find an expression for this Jacobian to then evaluate the Jacobian vector product and find a closed form expression for the propagation to our L dot. So for this, let us take a look at this first Jacobian. So let's derive the function L with respect to the input y. So we'll take the derivative with respect to y on 1/2 and then the L2 norm squared of the difference of y and yr. And now interestingly, we can also express this L2 norm, or more precisely this squared L2 norm, as an inner product between the difference vectors. So in other words, it can also be written as we find again the derivative with respect to y, so this doesn't change. But here we will have 1/2 times y minus yr in brackets transpose multiplied with y minus yr, and then closing that down. But even in that particular form, it's a little bit non-trivial in how to do the derivative of this expression. So I think it is more helpful to do it in index notation. So let's do that in index notation. And in order to do that, we will say we take the derivative of the loss, which is a scalar value, so it does not have any indices here, with respect to yi, with respect to the ith component of the vector y, which is an input of it. So this is the derivative with respect to yi. And now let's express the L2 loss in terms of its index computation. So essentially what that does is we again have the factor 1/2, but then we have a summation over all the entries in our vector. Let's have that go from 1 to n. And then it sums over yj minus yjr in brackets squared. So we take a difference, square it, and then sum up all the components, multiply it with 1/2. Okay, let's propagate this derivative operator into that. So first, it propagates over the 1/2, it is just a factor. Then it also propagates over the summation symbol, because differentiation and summation are both linear operations, so we can swap their orders. And as such, we will get 1/2 times the summation from j equals 1 to n of the derivative with respect to yi on that expression, which was yj minus yj reference in brackets squared. And now we can apply that one here. So let's do the chain rule. We first have an outer derivative and then an inner derivative. And these will be, so we will keep the 1/2 and also the summation from j equals 1 to n. And then we have first the outer one, which will be 2 times yj minus yj reference. And then the inner derivative is the derivative of yj with respect to yi. And whenever we see that, so, or in other words, whenever we derive a vector quantity with respect to itself, we will get the identity matrix. And here we will see if we derive an entry of the vector y at a different index position. So for instance, at index position 2 with respect to index position 3, this will be 0. And it would only be 1 if it was identical. And we can express that in terms of the Kronecker delta and say this one is Kronecker delta ji. So in total, we will then have 1/2 times the summation from j equals 1 all the way to n of 2 times yj minus yj reference multiplied with delta ji. And then our Kronecker delta induces an index change, and as such we will turn all j indices into I indices. And when we do that, we see that this summation will also vanish, because as such we only have one contributing summand, because if j was any different than I, this summation would have 0 terms otherwise. So let's say, for instance, I was 2 and this j runs from 1 to n, then if j equals 1, the summation will be 0. If j is 2, it will not, because then those are identical. If j was 3, it was 0 again, all the way to n. And as such, the summation breaks down into only one summand. And as such, we have 1/2 times 2 times yi minus yi reference, and then a 2 and the 1/2 cancel, and we just have the yi minus the yi reference. And I hope this also made a little bit sense why we keep the 1/2 here. It's kind of a self-fulfilling prophecy that later on we will get a factor 2, and it does not look nice, so let's just cancel it out. So it would also be a valid loss without the 1/2, but here it is for mathematical convenience. And this is in index notation. Let's go back to symbolic notation. So let's say back to symbolic notation. And if we see that the derivative of L with respect to yi is yi minus yir, we can see this is just the difference of the vectors. So we see that the derivative of L with respect to y will therefore be y minus yr. And interestingly, if we take the derivative of L with respect to the reference solution, we will get that swapped. So we will get yr minus y. And if you look at the derivation, we see then the inner derivative in that particular case would not be the derivative of yj with respect to yi, but it would be of the derivative of minus yj reference with respect to yi reference. And here we would get a minus sign, and this would then swap the order in our subtraction. Or so we could also write this as minus y minus yr. Now that we found the expression for the Jacobian, we can plug this back into our general definition of the Jacobian vector product. And this will then give us that the tangent on the loss is that expression, so y minus yr multiplied with y dot, and we need to do some contraction here. So let's have the transpose. So this is an inner product in order to contract that down into a scalar, plus this one here. So this will be, let's take this form. This will be yr minus y in brackets transpose multiplied with the tangent on the reference vector. Even if that sounded a little bit ad hoc to introduce the transpose here, you can also see that if you look at the numerator layout, if you derive a scalar with respect to a vector, you would actually get a row vector. So this would be in brackets transpose and here as well. But this is just a little bit loosely because we have to ensure that our dimensionalities match. And now with the expression or the closed form expression for the tangent on the loss found, we can write down the full push forward rule. And this means we can forward propagate tangent information on the loss computation given primal inputs y and y reference, as well as tangent inputs y dot and y reference dot, in that we first compute the primal, which is 1/2 times y minus yr in brackets or the L2 norm squared. This will be our primal output L, and then we get the propagated L dot in that we do exactly this computation. So we will do y minus yr in brackets transpose times y dot plus yr minus y in brackets transpose times yr dot. And let me close the brackets here. This in total will then give us L dot. Just some computational considerations. When you would compute the forward pass, you might want to do the element-wise difference. So you would compute a delta. So let's say you could compute a delta y as being, or a delta y vector by being y minus yr. You could reuse that quantity here, so you wouldn't have to do the subtraction twice. And another remark is that oftentimes you do not have tangent information on the reference, because often the reference is something that is rather fixed, but we derived it here with a tangent on the reference in more generality. And I just want to note this down. So often we do not have tangents on the reference. Or in other words, often this, and by this I mean the tangent on the reference vector, is the 0 vector. And as such, the second part in the computation would vanish or would just be 0. And this is the full push forward rule, which you would do in forward mode automatic differentiation over your L2 loss. But often for a lot of computations you would rather want to do reverse mode automatic differentiation in order to have the constant complexity with respect to some parameters. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more awesome content on automatic differentiation, like an example implementation on how to use various push forward and pullback rules in order to build an automatic differentiation engine in order to then train artificial neural networks, which is the essence of deep learning. Here you will now find similar videos, and I hope to see you in one of the next videos.